So as I promised from previous weekend, I want to talk about MINE, which stands for Mutual Information Neural Estimation. And it is written by Aaron Corville. He is one of the founders of GANs and works in Mila and CIFAR as well. And what is the motivation behind this article? So we can use it for very different problems. For example, we can use this for feature selection. As you know, it's a big topic. Feature selection is a big topic. And also explainable AI, which has several methods for explainable AI. So it is very important. Indirectly, we can use it for several problems. And for example, in any problem, you have an encoder. So you have trained that, and now you don't know the relationship between them. And you want to know in which, how if we know some part of Z, some points in the Z space, how can we reduce the uncertainty? How can we understand something about the input? For example, for example, instead of mutual information between X and Z, let's reduce it to think about X and Z. For example, X is just one dimensional. Instead of high dimensional input, we have just one dimension, and Z is just one dimension. So we just want to know. So think about it as a correlation between X and Z. We want to know if mutual information between X and Z is high or not, if there is some kind of correlation or not. Of course, mutual information is much more important than correlation because it captures nonlinearity. You know, in mutual information, X and Z, it is fixed. Your line is fixed, but if you think about it, it's a nonlinear way of correlation. But so it measures the uncertainty, and so how can we understand it? As I told you, it's very hard to understand to calculate mutual information. Historically very difficult. And it's a measure of true dependence, and it is tractable for discrete variables only because the sum can be computed exactly. And I of X and Z, I have written this for several times. It is h of X minus h of X condition on Z. So it is the KL divergence between XZ and PX, PZ. But we know from a very important theorem. It is called Donsker. We know from Donsker-Varathon that the KL divergence between P and Q, you can write it as just supremum over all maps from omega to R. And what is T? I told you we have an encoder, we have X, we have Z, we have encoder. So we can think about it as a black box that has input X, input Z, and outputs T. So your neural network is here. So depending on X and Z, you have a T. But the supremum over all expectations of all of these T minus log of expectation with respect to Q of e to the T, not T, e to the T. So using this, you can calculate the KL divergence between P and Q. And this is a good lower bound. So we can write the KL divergence between P and Q to be greater. So it is at least the supremum of EP of T minus log of EQ of e to the T. Of course, you know that in the F divergence, we don't have a log. So the difference is just one log. And the bound is tight for optimal functions t. Optimal function is t star. So for t star, so the bound is tight for t star. That relates the distributions to the Gibbs density. So if we just know that this is e to the t star is the optimal, and z is just the e to the expectation of e to the t star. So you got what I mean by this black box, because we don't know theta, and theta is the parameters of these neural networks. So if we give x and z to these neural networks, and the measure is I theta of x and z, and this is a real number. And this is a real number, you can calculate it. So because of that, Donsker-Varathon expectations are estimated using empirical samples, and you know everything. And then I of x and z, so it's a lower bound. So it's just, we need to maximize I theta of x and z. And so if p hat is the empirical distribution associated to n IID samples, then we can easily calculate x, z to be supremum of expectation. But now it's just Pn of xz, t of theta minus log of expectation of e to the t theta. And so in your gradient descent or subgrade or stochastic gradient descent, but here we are just maximizing it, so it's just gradient ascent. So it's just stochastic gradient ascent. So v theta is just 1 over b, I from 1 to b, t theta of xi, zi minus log of 1 over b, I from 1 to b, e to the t theta. And so we have v theta, and we just need to know the gradient in any stochastic gradient method. You just need to know the gradient, and the gradient is this g theta of the. The gradient of v theta with respect to theta is this. But if you work on this, you may notice that it's just the expectation of gradient of t theta minus expectation of, assume that we have a mini batch B, gradient of theta t theta e to the t theta divided by expectation of with respect to your mini batch and e to the t theta. So the problem is that this mini batch, full batch gradient estimate is biased. Because this is biased, people use you can reduce the bias by just replacing this denominator by exponential moving average. So this one, replacing it by exponential moving average. So using this gradient, you can find the parameters, this theta parameters of this black box neural networks. So it is as easy as this. The next article I want to explain today is just InfoGAN, but some people may not know the GANs. So I just review the GANs before I go to, because InfoGAN uses mutual information. And mutual information is the building block of my playlist, deep learning. Information theory of deep learning. So first I explain GANs, then I explain infogans, then so you understand how we can use mutual information in different algorithms. So general adversarial nets, this is a 2014 article by Ian Goodfellow and Yoshua Bengio, and the idea is that you have a generator and you have a discriminator. So you give the noise to the generator, you have noise, complete noise. So from a complete noise, I want to give it to a generator and create some g of z, and I want to say that if this is fake or not. The discriminator can either get original data, original images from MNIST, for example, or the generated MNIST data. For example, this could be 1. For example, it's generate number 1, original data in MNIST, it's number 1, and we want to fool this discriminator, and we want to say if it is fake or not. So check if it is fake or it is real. And you can do it with PyTorch very easily, and even InfoGAN I have implemented in PyTorch, but it is very difficult to get. Still, it's very difficult to get very good answer in very few epochs. And if you change even the batch size, if you changed all the parameters, and then you notice that you should select good hyperparameters in order to have a good answer, to have a good picture. Good, for example, MNIST picture. So we have 2-player minimax game. As I said, we want to minimize overall generators, maximize overall discriminators. The value of generator and discriminator, which is the expectation of X if you generate from P data, original data, of ln of D of X, plus expectation Z, noise could be generated from Gaussian noise or anything, ln of 1 minus discriminator acting on G of generator of the noise. So you should know binary cross entropy function, and binary cross entropy function is just it's just I from 1 to n. yi is label, log of p of y. It's just elementary deep learning. This is the probability plus 1 minus yi, log of 1 minus p of yi. So it's just binary cross entropy. And so our loss could be minus I from 1 to n. Yi is the ground truth, so it's our label, ground truth. ln of yi hat, which is our predicted probability of yi being original, which is integration of px, p data, ln of dx, because d of x at the end of the day is just the probability. And plus 1 minus yi ln of 1 minus yi hat. So notice that when we are passing original data, y is equal to 1. And y hat is equal to d of x. And then your loss is ln of d of x. But when we are giving fake data, I mean, you are using the generator, the neural network generator. So y is equal to 0. And it gives y hat equals to, you pass the generator to the discriminator. So the loss is just ln of 1 minus d of g of z. And knowing this, you can now train the loop. So we fix the learning of your generator. For example, until this iteration of what epoch, you have fixed it, and after that you have an inner loop for discriminator. So you take m samples and m fake data samples. You update theta d by gradient ascent, because you want to maximize it, because we want to maximize value function with respect to the discriminator. And here we have derivative with respect to theta d, 1 over m ln of d of x plus ln of 1 minus d of g of z. So now we fix the learning of d star. Here we fixed for the generator. Now we say until this epoch, until this iteration, fix for discriminator. And then we take m fake data samples, and we update theta g by gradient descent, because we minimize value function with respect to g. That's why here we have gradient descent, and at that time we had gradient ascent, because we were maximizing. Here we are minimizing. And finally, so it becomes 0, because 0 is just because derivative with respect to parameters of the generator neural networks of ln of d of x is 0. It doesn't care, it is fixed. And this 0 plus derivative with respect to the parameters of the generator neural network, 1 over m ln of 1 minus d of g of z. And that's it. This is the algorithm. So for every k updates of the discriminator, k update for discriminator, we are updating generator once. So this is very important. And for fixed g, the value of the generator and the discriminator is the integration over p data ln of d of x plus pg of x generator. And you know that domain of x and z are the same, ln of 1 minus d of x d of x. So this will be maximum for, we know the maximum, d of x is just p data over p data plus pg. So using this, and I can prove something, and I can prove this in a moment. So we have value of d and g, you can write it as the integration of, what is the expectation of log of d of x? Is just p data of x.